We're awash with misinformation spread by social media and so on. So that the level of fake science and bad science and misinformation out there, the volume of it is growing rapidly. The only way to push back against that is by getting the right information out there simply and clearly. The annoying thing, I think, is that it just persists. There are things that have been debunked heavily and
over and over again,
over and over again, and then they just keep coming back. Like, why are we still even talking about flat Earth? How people have searched for certain terms, and I put in all the pseudoscience terms, and it's kind of shocking how they mostly are increasing. Flat Earth, astrology, levitation. You can pick your favorite fake science or pseudoscience, and government. The idea that many people could keep a conspiracy theory secret, that we never went to the moon, it just boggles the imagination. So I don't really truly understand why some people would believe that. And in the US, it's about 8 or 9%. So some things persist just because the authority. The stereotype of science is that it's not very creative. It's just mechanistic and working through equations. And the universe is a little more creative than humans are, and has come up with some amazing things that we've discovered and tried to understand. So that sort of emboldens you to use your imagination. Imagination is what binds all the different disciplines together. So creativity and art and science, I think, are fundamentally the same thing. We're trying to prove ourselves wrong as fast as possible because that's how we make progress. That's Einstein himself, as the architect of the theory that can predict and understand black holes, didn't think they were real. He thought they were mathematical artifacts. When you get an infinite quantity in physics, that means your physics is wrong. And that's the place we still are, actually. Black holes are not fully explained. Eventually, these far future civilizations will be huddled around black holes to get the last energy available to them. It's just possible that as scientists, we may not be smart enough to figure this out. But some things may be beyond our grasp, and we might have to accept that. You can have clever ideas, and you can be a theorist, and you can use your imagination as much as you want. But in the end, until you compare it to reality with an observation or an experiment, it's not science.
Hello and welcome. I'm Yazan, and this is Parallax, Inside Creative Minds. For thousands of years, human beings looked toward the night sky to follow the seasons, navigate across land and sea, and to give structure to the passing of time. But they also looked upward in search of knowledge and meaning. The night sky was a clock, a calendar, a compass, and one of humanity's first great mysteries. From that long practice of watching, recording, and questioning grew astronomy, often called the oldest science. Today, it draws upon physics, mathematics, chemistry, geology, biology, and computer science to investigate a universe far beyond ordinary human experience. Astronomers can determine the distance of a star from an almost invisible change in its position. They can read the chemistry of distant objects from their light, detect planets they cannot see, calculate the mass of an invisible black hole, and listen for collisions that occurred more than 1 billion years ago. How can such small signs reveal such enormous realities? Astronomy faces a peculiar challenge. Almost everything it studies lies beyond our reach. We cannot carry a star into a laboratory, repeat the beginning of the universe, or watch two black holes collide from neighborly. Instead, astronomers work from traces, ancient light, the movement of an orbiting body, a distortion in spacetime, or a tiny shift in an angle called parallax. This is the ingenuity of astronomy, making the unreachable measurable. And that requires imagination. Before something can be discovered, someone may first have to imagine how it would reveal itself. What traces would an unseen planet leave behind? How could we recognize an object that traps light? What would reach us from the collision of two black holes? But imagination becomes science only when it meets evidence. A scientific idea must face observation, criticism, and the possibility of being wrong. Science gains its power not from claiming certainty, but from testing its own ideas, correcting its mistakes, and leaving its knowledge open to revision. And that distinction matters increasingly today. We live at a time when scientific knowledge is becoming more precise and more complex, while suspicion of scientists, universities, and institutions continue to spread. Conspiracy theories and pseudoscience often offer certainty without demanding any evidence. So, how can scientists communicate complexity without merely asking the public to trust authority? And how can skepticism remain a tool for discovering truth rather than becoming an exercise for rejecting knowledge? Black holes bring imagination, evidence, and mystery and all of that together. They were imagined long before scientists possessed the theories or instruments required to understand them. Today, we can measure their mass and motion, observe their effect on surrounding stars, and detect ripples in space-time produced when they collide. Yet their deepest mystery remain unsolved. What lies at the center of a black hole? What remains after the final star exhausts their fuel and galaxies grow dark? Could civilizations in the far future survive by drawing their last available energy from a black hole? Astronomy reaches backward toward the beginning of the universe and forward toward its possible end. It reveals how small we are, but also how far the mind can travel. Creatures living briefly on one planet can reconstruct the history of galaxies and detect events those signals began their journey before humanity existed. Artificial intelligence may help astronomers discover patterns hidden within oceans of data. But can it produce the kind of original ideas that changes our understanding of reality? And how far can any intelligence go? Will science eventually uncover every mystery? Or are there parts of the universe that the human mind may never be equipped to understand? As knowledge expands, what happens to wonder, to faith, to the mystery that first draws us toward the night sky? My guest today is Chris Impey, University Distinguished Professor of Astronomy at the University of Arizona's Steward Observatory. His research spanned observational cosmology, galaxies, quasars, gravitational lensing, and the intergalactic medium. Across more than 220 refereed publications, he has used major ground based observatories and the Hubble Space Telescope to investigate some of the universe's most distant and mysterious phenomena. He has received 11 teaching awards, and his audiences have ranged from university students and NASA engineers to school children and Buddhist monks. His online astronomy courses have reached hundreds of thousands of learners around the world. He's also the author of 10 popular science books, including How It Began, How It Ended, Einstein's Monsters, and World Without Ends, as well as the science fiction novel Shadow World. In 2026, he received the Lewis Thomas Prize for Writing About Science, an international award honoring scientists, those whose work brings science and the humanities. So here's my conversation with Professor Chris Impey, and I hope you enjoy it.
We are a way for the cosmos to know itself.
This is Parallax, conversations and interviews by me, Yazan. I talk with academics, scientists, thinkers, and all creatives, and I'm here to listen, ask questions, and learn from their insights.
Drawn by the music of cosmic harmonies, it can take us anywhere in space and time.
To better understand how the world works. And we are recording. Professor Chris Impey, thank you so much for being here. I've been waiting to talk to you. I'm very happy to finally talk to you in face. Welcome to Parallax.
Yeah, well, I'm glad to be here. Thanks very much.
It's satisfying to me to ask you first before we get into anything. The name of this podcast, I made a list of names, maybe 25, and then I decided it's going to be Parallax. I know a little bit about that, and as you know, it comes from astronomy. Can you tell us? In my view, it's important thing because I come from the world of art and music composition, to speak to people who are in different places and domains. Can you tell us shortly what is parallax?
I mean, parallax is a way in astronomy of measuring distances through angles. So it's fundamental to how we measure the distance to anything. So basically, in astronomy, when people were trying to figure out how far away the stars were, which was for hundreds of years after the telescope was invented, we had no idea of the distance to the stars. Um, but eventually, the way you do it is you observe stars when the Earth is on one side of the orbit than the other, and that the two different perspectives create a little skinny triangle, and you measure the angle, the skinny angle, if you like, from two measurements 6 months apart, and then you have the distance, and so that's the parallax angle. So it was a fundamental tool of figuring out the size of the universe, really.
Exactly. The simplest example is perhaps people talk about when you put your finger and you try to look through different eyes. Any important example from astronomy comes to your mind about that, that demonstrate any significant of the significance of this?
Sure. I mean, you're right. The best example we're all familiar with is binocular vision. So our brains interpret the distance to things based on the fact that we have two eyes. And so our brain is essentially looking at parallax when it does that. If we had one eye, we wouldn't be able to do parallax measurement, and we'd be very uncertain how far away things were. So the human eyes are a good example. In astronomy, probably the best example was people didn't really know how far away the stars were. So going back to the ancient Greeks, nobody could measure the parallax angle of stars because it turns out they're so far away compared to the size of the Earth or the solar system, that unless you have precision tools, you can't measure parallax angles. So these are just very, very small angles and difficult measurements. So unlocking the key to the size of the universe, going back to the ancient Greeks, depends on the idea of parallax.
When I look at your work and your life, it's so rich and you have galaxies of many different things. You're one of those people who it's really hard to decide where to start with, or what subject to choose, or where to maybe 9 books so far. You taught astronomy. You started as a physicist, my understanding is, and you traveled to teach monks and Buddhists, and lectured every year for NASA engineers and so forth. I'm interested to know how all of that started for you, and start to take you eventually into
Sure.
astronomy.
I mean, without getting too extensive on the history, for many astronomers, physics is the first training. So my bachelor degree was in physics from the University of London. And so if you like, physics is the gateway drug to astronomy, because once you know physics, then you start applying it to understand the universe, and that's astrophysics or astronomy. So it was a very appealing thing once I had a background in physics. And there was a golden age, there still is a golden age of building large telescopes on the ground and some pretty impressive space telescopes. And so astronomy was booming. The research in astronomy was, while I was coming up, was very exciting. So it was an easy field to become a part of. And that hasn't lapsed, actually, that there are new telescopes and new discoveries every week or so. So astronomy is a very active field.
Yeah, exactly. I want to move a little bit to imagination as a concept. That's my next question. I want to connect that to many fields, maybe throughout this interview. I uh, I one day I wrote about I've read Johannes Kepler's Somnium, and then I was listening to one of your audiobooks, the latest book of yours. What was it? Worlds Without Ends. You also talk about Somnium. I was struck how Kepler in the 1600 was able to imagine the moon, its geography, and travel there. And I even translated that into Arabic, and I made video about it. And it makes me feel about the importance of imagination. But he also wanted maybe to convey his ideas to the audience that wouldn't take, in my understanding, wouldn't accept the model, the heliocentric model.
Mhm.
Can you speak about imagination? You also wrote fiction. Maybe we'll go into that. But how do you see the parallels? Where do they intertwine? Scientific imagination, artistic imagination, or otherwise?
Yeah, I mean, I think imagination is very important to science and to scientists. It's particularly important in astronomy because most of the things we found out about the universe were unexpected. They were surprises. They were discoveries. So um, the universe is a little more creative than humans are, and has come up with some amazing things that we've discovered and tried to understand. So that sort of emboldens you to use your imagination because whatever you can imagine, the universe may well have already created, and so it's a liberation to use imagination. And as you point out, imagination is what binds all the different disciplines together. So creativity and art and science, I think, are fundamentally the same thing. The stereotype of science is that it's not very creative. It's just mechanistic and working through equations and applying strict rules to things, and that's sort of there's part of that for sure. But it's also got some imagination involved. I mean, then Kepler's a good example. That was very the first science fiction, you might argue. But a lot of people were trying to use their imagination to understand the universe before we had it. The exoplanets were discovered 40 or so years ago, and before that, space artists were imagining exoplanets and life on other worlds. Just we didn't have the capability to look for those places yet, and then the science has started to catch up.
But especially in, I mean, especially in astronomy, but also even people imagining atoms, the endless universe. Bruno, who imagined the endless universe, right? But in astronomy, I guess you wrote about this, that it's not. People tend to think that science is just about those solid, cold ideas, and but I remember reading something you wrote that all you need sometimes is less, way less than like big telescopes. Of course, you need telescopes and tools, and but then sometimes you need just a good idea, right? In
Mhm.
astronomy, any example comes to mind how an astronomer or a scientist needs sometimes only a good idea, or to rather than the biggest telescope, or
Right. Yeah, I mean, yeah, ideas. Well, Einstein had that great quote. There are a lot of things attributed to him, or not actually things he said, but he did say imagination is more important than knowledge, and that's a pretty profound statement coming from him. So I think scientists have used their imagination sometimes to solve uh, very hard problems that don't you can't have an observational access to that. You use your imagination to understand um, how to solve the problem. I mean, a good example from physics that goes into astronomy is our thought experiments. And thought experiments, they go back to the Greeks. They go back to the beginning of science. The Greeks didn't have experimental tools, of course. They had no telescopes and microscopes. Um, but they used thought experiments to try and make arguments about whether the universe was finite or infinite, or about whether atoms were real. Very profound questions. And then into the 20th century, astronomers or physicists especially are still using thought experiments. They're using them to work with the new and mysterious and strange quantum theory to try and understand the nature of reality. So because and that's those are still profound questions that haven't properly been answered. So thought experiments is it's just a tool of science, but it immediately involves imagination because you're trying to imagine an experiment that may not even be possible or might be possible in 100 years because you think it might tell you something important about the universe.
yeah. Maybe last question about imagination. You wrote science fiction novel. I wonder how was that, and at what point did you decide to do that, and if there's any motivation other than pleasure, discovery, and do you see imagination? Were you fighting anything as a scientist who was just jumping suddenly into a complete freedom of world of freedom, or how do you navigate those two things?
Sure. I mean, I did that. I mean, I had little time spent on fiction since then, but mostly I'm writing standard science nonfiction. That was an experiment. It was a sort of a fever dream. I had a month and a half in the summer set aside. It was brutally hot. Couldn't really go anywhere in Tucson, and so I just holed up and pretty much ground out a crazy amount of words per day and wrote this whole book in about a month. In a kind of strange altered state because I
And
wasn't
one
sleep.
month. Wow.
Yeah, I wasn't sleeping much. I was things were coming into my head. The writers talk about this kind of fugue state you can go into where things come into your head and things are fully formed and the characters are speaking and you just write down what they say. And I don't usually experience that, but when I was writing that book, it did happen. Now it is a very experimental book. I wanted to play with fiction. I wanted to play with space, time, reality, sort of profound questions, and then express them through the journey of a narrator or a character. The book is designed deliberately to be a little challenging. There are disconnected pieces of the book, dislocations in time and space that the reader has to sort of put together and be a little patient to realize what's happening.
I'm glad
Um,
you just said that. I'm gonna listen to it. Shadow Worlds. So where do you think this flow how, did all of those ideas come from? Is it from your scientific training, or is it just suddenly burst of freedom? Or
Yeah, it's sometimes you get out of your regular mold. I mean, I'm in a university, so I teach, and there's a rhythm to working in a university. A lot of meetings, administration, bureaucracy, teaching on a
yeah,
fixed schedule. So just liberating yourself from the schedule helps. As an aside, that's one of the reasons I enjoy every year or so going into northern India or other places to teach the Tibetan monastics because I'm essentially off the grid. I'm off the clock. I'm not doing my usual thing. I mean, yes, I'm teaching, but that's about all. The rest of it is very free form, and that's sort of liberating. So I do enjoy that mode, and it's not what a standard scientist experiences or a standard academic. Sometimes it's nice. I mean, artists and purely creative people get to experience it more because that's sort of their life. Musicians and artists. For scientists, you have to force open that space, and I was quite happy to be able to do that.
yeah. And but you also you love, I assume, science fiction. I asked you before when I took your class. You read a lot of science fiction. I don't know if it's for joy, but you reference it in your writing and your lectures, so it means something to you. But now I want to move from science fiction to real science. As I told you, I took your class maybe 2 years ago, and it's a great class to understand astronomy. It's full of fascinating videos and all of that. And I remember now, I want to bring this up, that the first chapter, perhaps it was about the scientific method. So I was preparing to go take a class about astronomy, and the full first chapter was about the scientific method. My question is, can you lay out to me what is the scientific method, or what are those principles if we would communicate those to the public?
Right. It's foundational to me for all of science, so I tend to put it first when I teach astronomy or in a video course. Yes, it's important. Um, you know, Scientists have a way they approach understanding the universe. That could be the miniature universe inside an atom or the big universe out there. Um, it is rooted in observation and experiment. I mean, there is no science without observation and experiment. I mean, you can have clever ideas and you can be a theorist and you can use your imagination as much as you want, but in the end, until you compare it to reality with an observation or an experiment, it's not science. So that's the first thing that's found. It's rooted in observation, empiricism. The second thing is, which is great boon of science and why it's a powerful method of understanding the world. It's based on free and open communication. Everything is transparent. The journals, of course, they have paywalls now, so it's kind of obnoxious that people have to pay to publish and pay to see the stuff. But increasingly, there's enormous amounts that are online in the archive and so on. Now, the average person's not going to read technical papers, but they're available. Everything is available. The U.S. government mandates that these things be available. So, and scientists spend all their time communicating. They write papers, they go to conferences, they collaborate in big groups and email each other. So that to and fro of science and open communication is it's foundational, and it's why it's fun, because you feel like you're part of a worldwide community. I have collaborators and colleagues all over the
And
world,
just
and
a little point here before we move. Uh, I heard you speak in one interview about that even scientists have responsibility on one level or another to communicate those ideas, because there's some popular understanding that there's this ivory tower or this authority that is called the scientific establishment, and there's hostile feeling against it. Can you, and you feel that maybe they're paid for it, maybe they're not, but they eventually they're doing this science for a reason, right? Which is to communicate that, and so there's
right.
nothing hidden out of from the public. And
No, I mean, a lot of scientists spend a good fraction of their time communicating. It's, at a very technical level in their subfield, and that's probably an impenetrable conversation for the general public. But most scientists in the industrialized world are paid by the taxpayer, and so I think they therefore have an obligation to communicate, because the bills are being paid by people who are not scientists, the general taxpayers. So that's one reason. The second reason is we're awash with misinformation spread by social media and so on. So that the level of fake science and bad science and misinformation out there, the volume of it is growing rapidly. And you have to the only way to push back against that is by getting the right information out there simply and clearly, to the biggest audience you can find. So that's the second reason. And then the third reason is it's kind of fun to communicate with to take a difficult idea, something like relativity that seems very abstract and technical, and be able to communicate it to a larger audience. So it's a challenge, and then it is true that many scientists choose not to do very much of that. They just say, "Well, that's not my skill set, or that's not what I'm good at." Um, I think if everyone did that, we'd have a big problem. So I think more scientists actually should be out there communicating more broadly.
yeah, perfect. So this brings me to the other side of the coin, which is pseudoscience. Now, I'm not a scientist, but I really get mad when I see this. I don't know what to call it. Today we have like those Netflix shows about alien and building the pyramids,
Mm.
flat Earth societies. That goes on and on. I mean, uh, do you get mad at this? Before we talk, I mean, before I ask you how do you fight that, but don't you doesn't get your blood boiled or scream? You want to
Sometimes.
scream at people or
Yeah, but I'm in that world so often, I can't afford to raise my blood pressure that way. So, yes, I do get mad at some of it. I get frustrated, or I just take a deep breath and say, okay, let's try and combat this. And some of it is, people believe strange things. It's not even necessarily about science. A lot of misinformation these days is in the health arena. And that's dangerous. I mean, being a flat earther is extremely anachronistic and a very wrong-headed idea, but it's not going to get you killed or hurt you. And misinformation in medicine is really dangerous. So the misinformation is, has some areas where it really is a problem. In science, it's a problem for sure, because they're hearing things that are just not true. The annoying thing, I think, is that it just persists. There are things that have been debunked heavily and
over
well,
and
like,
over
and
again? Yeah,
over and over again, and then they just keep coming back. Like, why are we still even talking about flat Earth? To your web searches, it starts in 2004. So we've got a 20-year run at how people have searched for certain terms, and I put in all the pseudoscience terms, and it's kind of shocking how they mostly are increasing. Flat Earth, astrology, levitation. You can pick your favorite fake science or pseudoscience, and people are searching on that stuff.
creationist, and it
They're
goes on and
interested.
on. I was thinking even,
The one that annoys me the most, I have to say, is
yeah.
the Apollo deniers, the people who think we never
Oh
went
yeah,
to the moon, which is a crazy thing to do. That the fact that, because it involved hundreds of thousands of people working for thousands of companies and across the federal government, the idea that that many people could keep a conspiracy theory secret that we never went to the moon, it's just boggles the imagination. So I don't really truly understand why some people would believe that. And in the US, it's about 8 or 9%.
Chris, I could tell you why this one is a little bit, because you're an astronomer, you know everything.
No.
This one is a little bit tricky for the average person, including me. I had to go through many things. I wasn't denying anything, but to debunk every single thing, it takes a little bit of knowledge, as it's not as simple as being a creationist or being flat earther, right? But I would thinking even from the time of Galileo, my next question still here is, why do you think those things persist? Why do those pseudoscience stories, superstition, and those things survive? Galileo took the telescope and he looked and he draw what he saw, and he told us what he saw. And then hell broke loose, but he invited everyone. You wrote about this as well. He just told them to come and see for yourself. And even after they saw what he was speaking about, the geography of the moon,
Mhm.
the moons of Jupiter, etc., people just said no. So you also study education, right?
Right.
You have papers on education. You're involved in education deeply. What is it? What are the main things for some people to change their mind? Is that the difficulty, or is it bunch of or failure of communication? Or,
I mean, it's a failure of education too. I mean, if we could go to back in historical examples, Aristotle was a brilliant philosopher, of course, but most of his physics was just wrong.
Mhm.
And even at the time, it was known that that was wrong. And then after it was proven to be wrong, people still thought Aristotle was such a great philosopher that he must have been right about that. So some things persist just because the authority, people believe a certain authority over another authority. Um, so that's part of it. And the other part of it is maybe the stakes are low. If it's not a medical thing, I mean, if people want to believe in astrology, which is a pseudoscience, which has no planets in their positions, sun and moon at the time of your birth or through your life, has no bearing on what happens in your life or your personality or anything. That's been debunked heavily over centuries. But there's a lot of people who still believe in astrology, especially in the West, especially in the US. Um, and that one doesn't bother me so much because I think it's a very low stakes belief system. Most people are not going to make major life decisions based on their horoscope. Maybe a few will. Um, so, at some point you just have to say that people are complex. They don't have to. They don't have to. They don't behave fully rationally in many areas of their life, actually. And maybe you'd squeeze all the fun out of life with every decision that you could possibly make based on evidence and rationality. That would be a sort of very antiseptic way of living. So I see the danger of sciences, if you like. I also think in the modern world, there's a new strain, which is this sort of rebelling against the elites. So scientists, professional scientists at universities are considered an elite. And there's a tendency to say, well, they don't really know anything at all. And so, the questioning authority, which is not a bad thing in general, has become a strong strain, especially in the United States.
it also justifies one's ignorance, right? Rather than understanding some topic, just say this is the establishment, I'm going to go against it, and so forth. But it's also important to make this distinction. Maybe you would, that science is not authority. In fact, it's maybe they're humans, but eventually it's just a self mechanism, correcting mechanism, right? It's all about skepticism and proving others wrong. And would
Right.
you
I
put it
mean,
that way?
there's another quote from a famous scientist, Richard Feynman, physicist, said, "We're trying to prove ourselves wrong as fast as possible because that's how we make progress." That's a nice way to sum it up. Yes, all the knowledge is contingent. Everything is up for grabs. You keep asking new questions, keep improving your observations, and acknowledge that what you knew last week or 10 years ago might be wrong. Hopefully, we're converging on something that we can call a collective truth and wisdom about the universe. But there's things with cosmology and dark energy and dark matter. Some people feel our areas of ignorance are huge. And so maybe the whole enterprise is flawed at some level.
Yeah, you perhaps end up with less friends if you follow. That would be the consequence if you keep proving your friends wrong, right? I want to move a little bit to more serious question. I finished Einstein's Monsters. It's such a beautiful book. I have to admit it's demanding, but it's also rewarding. I want you, Chris, to take us through, if you don't mind, because you're a storyteller. I first learned to black holes. I first learned when I learned how they work. I was absolutely fascinated from the escape velocity equation until everything you worked with on black holes and supermassive black holes. I think that story is really beautiful. It's a story of human endeavor and discovery. And can you walk us from the moment, I don't know what was his name, the escape velocity, to Hawking, Oppenheimer,
Sure.
Einstein,
Well,
please?
briefly, I mean, it's an example of imagination. So long before relativity and Einstein, which is what you need to understand and predict black holes, this English clergyman, John Mitchell, he just used Newtonian physics to speculate about dark stars. Just imagine, well, he knew about escape velocity, that idea. He just said, well, what if you had a star that was so massive or dense that the escape velocity was the speed of light, the fastest thing there is? It would be a dark star. And that was hundreds of years before the proper tools to understand black holes.
That's
Right.
kind of very strange. Okay, so
Right.
he thought this with Laplace, I guess, at the same time. Or
Same time as Laplace. And then that idea sort of goes dark, if you like, for a while. And we don't really make progress until general relativity. And then the title of my book is, of course, a reference to the fact that Einstein himself, as the architect of the theory that can predict and understand black holes, didn't think they were real. He thought they were mathematical artifacts. So that's very interesting. He didn't have enough confidence in his theory, although it had been tested very quickly after he published it. And indeed, it took decades before the first black hole was discovered, not till the late 1960s, because it's obviously very hard to find something that's dark and very small and very far away. But it's a wonderful story of discovery in that history of science, where a theory can have this kind of bizarre prediction, and then eventually you find out it's right. And then not only do you find out that dead stars can be black holes, but you can have black holes that are very much bigger than a star and very much smaller than a star. Nature could make black holes of a fantastic range of sizes. They're all possible in principle.
yeah, a few steps were also there after Einstein publishes the general theory of relativity, maybe 1915. Who was the scientist who find the solution? And then Oppenheimer, slowly all of this story until you guys in astronomy finally, would you say the final step, the final big proof was the picture, or a little bit the picture we took, or a little bit before that? Like the
I mean, the first proof of black holes came through the 60s and 70s with binary star systems, where one is a dead collapsed star, a black hole, and the other is a visible star. That's your tool for understanding them. And that didn't make headlines particularly because it happened incrementally over a decade or so. But by the 1970s, we had 50 or 60 black holes that we knew were there, dead stars. The exciting and unexpected part was through the 70s and 80s when people found strange behavior in the center of some galaxies, and then they were led almost inexorably to the idea of supermassive black holes at the center of galaxies. So black holes, a billion times bigger than the sun, or in the case of the Milky Way, 4 million times bigger. And that was a surprise. I was shocked. But they're fundamentally the same kind of objects. Black holes are exotic and mysterious, but they're actually physically very simple objects because they're only defined by three quantities, however big or small they are.
Yeah, I still find this really strange, which is the spin and what's
The mass, the size, and the spin. That's it. There's no other property that you can measure or understand. But it's also important to remember that as good as general relativity was and is, and how it did predict their existence and allows us to understand them at some level, it doesn't fully complete our understanding. Hawking said black holes contain the seeds of their own demise, and he's referring to the singularity. So the theory does predict a cusp or an infinite mass density at the center of the event horizon. And that's not physical. That when something happens, when you get an infinite quantity in physics, that means your physics is wrong, you're missing something. And that's the place we still are, actually. Black holes are not fully explained by general relativity or by the theories we have at our disposal.
Yeah, so that was actually my second question. So you looked into black holes, right? And telescopes. We got singularities and then Hawking radiation and the problem of information lost. Can you walk me through that? But first, do you assume that once there's a singularity, meaning something infinite, whether it's gravity or the beginning of the universe, the end, does that mean that it's automatically wrong? I mean, one could think, I don't know, why not? Or
Just means a theory is incomplete because if you go back to, I was an undergraduate studying physics, and we were taught very quickly that in basic electromagnetism or thermodynamics or whatever the fundamental physics we were doing was that any quantity that has an infinite value is essentially nonsensical. That's not physical to have an infinite quantity. It's fine to have pure mathematics. There are many types of infinity in mathematics, and that's not a problem. But in physics and in the real world, the material world, infinite density or temperature is not comprehensible. It's not understandable. It just means your theory is incomplete. It doesn't mean it's totally wrong. It just means you need something more. So you're still working, and people are still working. The black hole theory is very active. Hundreds of research papers a year are still written on the theory of black holes.
yeah. So then came Stephen Hawking. You wrote about him. One line I remember you said, maybe that was I don't know if you were quoting or that's your line. You said he was staring all his life in the face of death, or he was looking at death all the time. That's a metaphor for. So what did Hawking do? You met Stephen Hawking also, right?
Yeah, when I was a student at Cambridge, and he still had the capability to lecture using his keyboard. His eyes would move over the keyboard, and he could pick out letters that way. It was very slow, and he had his famous mechanical voice. And the quote, just to give a proper source to the quote, in that book I was referencing a quote from Martin Amis, the British author, British fiction writer, who wrote a very clever detective story, like a noir detective story, which involved a scientist and alludes to black holes. So I pulled that quote from Martin Amis. So Hawking, made incredible contributions to black hole theory. He didn't solve all the problems. He didn't solve the singularity problem. Although with Roger Penrose, he came up with 3 singularity theorems. So we have as much as we can understand singularities in physics comes through Hawking and Penrose. He didn't understand the information paradox. He couldn't solve that. He was also very disappointed because Hawking radiation is so subtle and so difficult to detect, may never be detectable by astronomers. He was disappointed because, of course, you win Nobel Prizes for discoveries, not for theories. And if someone had managed to detect Hawking radiation while he was alive, he would have been a sure bet for a Nobel Prize.
My next question is about gravitational waves, another super cinematic story. You wrote about that, how, but I also then I found it in many documentaries. The moment those two events happen, I would like us please to walk us through this. You say in the book, almost every day a space-time ripple passes through your body to a binary black hole catalysm somewhere in the universe. It might approach from above or the side or below your face. You go about your business unaware of the thing. What are we talking about here?
So gravitational waves, another prediction of general relativity back from the origin of the theory. Also another prediction that Einstein was equivocal about whether he thought that was real or not. And most physicists for decades just thought, well, okay, it's such a subtle signature. It's a distortion of space-time that travel at the speed of light caused by a mass situation changing or a mass configuration changing. And binary black holes are just the most dramatic ways mass can reconfigure. And so they're the best source of gravitational waves, but not the only source. So it was just considered esoteric and undetectable. And so the experiment LIGO that did detect them was a tour de force. It was incredible. It's the most accurate physics experiment by 3 or 4 orders of magnitude ever. I still, given the funding landscape for science these days, I marvel at Kip Thorne and the other architects of LIGO going in front of Congress and asking for $1 billion for a machine that was detecting invisible space-time ripples that flex things by 1,000 times smaller than a proton. So, it sounds like a very hard ask for money from
Of
the
course, it
government, but
sounds
they got it.
crazy.
They got it. It's amazing. That was back in the good old days when Congress was bilaterally supporting science and people with clever ideas could get them funded. So that's what it refers to, these space-time ripples from black hole binaries throughout the universe. They are indeed passing through us, but our bodies are flexing or changing shape due to space-time changing by that infinitesimal amount, tiny fraction of the size of a proton. So we don't really feel anything.
Yeah. So just to paint it in a simple way. So two black holes collide. When was that? And then at the same time, life is happening on Earth. Human civilization is happening. The
Mhm.
Stone Age, then fire. Right? Is that true?
Right. So the first black hole event, the one detected a decade ago now, it was in a galaxy 1.3 billion light years away. So that black hole merger happened not just before humans. I mean, 1.3 billion years is before, there were only barely multicellular organisms on the Earth. Life was very primitive, nothing bigger than you could see with a microscope. So that's when those black holes merged. And a black hole merger is the most dramatic gravitational event you can imagine, because each of the black holes is an extreme distortion of space-time. And when they dynamically merge, they create these dynamical space-time ripples, if you want to call them ripples, that move through space. So that event happened an incredibly long time ago. And then luckily we built LIGO just in time to detect those mergers as that wave passes across the Earth at these two disparate locations.
Yeah, exactly.
So LIGO is based on two identical experiments separated by a continent, the width of the continent, to make sure that you can say it's astrophysical rather than geological, because there are all sorts of geological tremors and murmurs in the Earth. The Earth is a noisy place. So you have to filter out all the geological noise, essentially, to see astronomy signals.
Yeah, so this is one of the most beautiful stories for people to picture, that this ripple was moving throughout millions of years while our civilization was advancing. Then, the Industrial Revolution, whatever, Einstein publishes general relativity, and it's still moving until we build the LIGO, right? And then we detect it. But this doesn't mean that it's the only wave. I mean, right? If we were, let's say, late 50 years but I found this synchrony incredible. It's just one of those stories. Chris, I want to move to the end of the universe. How does it happen? But first, I want to just read you this another quote I love by the end of your book. The only music of the sphere is the low thrum of a black hole. Black holes spinning slowly, inexorably. They evaporate. This is the end. Why,
Right.
Chris?
Because there are phases of the universe. The universe we think is going to expand forever. The idea of a recollapse or a big bounce, that's not going to happen. It'll just get bigger, more diffuse, colder. And within it, the objects we're familiar with, stars, will eventually there'll be no new stars. And so galaxies will go dark. And that will happen in a few 100 billion years. The last feeblest stars will exhaust their fuel supply and go dark. And then we're left with stellar remnants and stellar corpses. Um, and then also, according to physics, our incomplete knowledge of physics, is quite likely that normal matter is unstable. Protons decay if you give them a long enough time. So normal matter will disintegrate, if you like. And so black holes, if that part is true, then black holes are the last repositories of matter, and they will be slowly evaporating and radiating according to Hawking's ideas. And the biggest black holes will last the longest. So the visualization I have in that part of the book is of a universe where almost everything is dissipated, where everything is dark, where the last repositories of matter are black holes, which are all spinning and they will eventually evaporate. You can also draw energy from a black hole that's spinning. Its angular momentum, its feeble radiation. And so if you want to know about the far future of life in the universe, eventually, when there are no stars, we won't live on planets lit by stars because the stars are all dead. So I think eventually these far future civilizations will be huddled around black holes to get the last energy available to them.
Yeah, so the further we approach the future, it seems like maybe because of entropy and thermodynamics, there's inevitable death. Maybe we're sure of that. But then some rebellion against that, physicists put forth, as you mentioned. What are they? So we need energy, obviously, even if consciousness managed to transcend physical bodies into some sort of a computational scenario where we just could exist as civilization. We still need energy, right?
Right. And the laws of thermodynamics are kind of implacable, and that part of classical physics has never been proven wrong in the modern era. And so the death of the universe is just an expression of the laws of thermodynamics, the tendency to disorder. And black holes, will thumb their noses at that for a while, as long as they survive, but eventually even they will succumb to the second law of thermodynamics.
Chris, my final question is about astronomy, the mystery of the universe, and what all of that provoke, what astronomy teach us, perhaps even thinking about God. And uh, does it seem to you that no matter what we know and more advanced, maybe the ultimate task of science is to uncover all the mysteries? But that got me thinking, what if we know everything, just like Laplace's demon? In Arthur C. Clarke, he imagines in 9 billion names of God. You probably know the story that
Sure.
once you know all the names of God, or to me, it's a metaphor of knowledge. Maybe there's
Mhm.
no more, there's nothing left, and then the stars go and the universe stops. And I want you to say something about uh, perhaps the ending in the shadow of ending, or if there's any ending. Uh, what does astronomy teach us, and also your ideas, if you can touch on God, on mystery and knowledge.
I mean, that astronomy is, especially among the sciences, is teaching us to be a little humble about what we know and think we know, because the large field of astronomy cosmology is filled with imponderables. It's filled with the fact that we don't understand dark energy and dark matter, which is 95% of the universe. The physical state of the Big Bang is not comprehensible. It's another singularity, therefore we don't understand it. What caused the Big Bang is not part of the theory, and therefore not understood. Whether there are other universes allowed by quantum creation of the universe, which is the current idea, that's not clear, and we'd love to test that. So cosmology is so full of huge questions that are unanswered, that as sophisticated as it is, and as powerful as our computers to simulate things and our huge telescopes, it's hard to see that it's the end of the road. I mean, that's why it's exciting. If you were just putting the last decimal place on a calculation, and that's all the future generation could do, that's what Kelvin said. He dissuaded young people from going into physics at the turn of the 20th century because he said physics is solved. There's nothing to work on. Who's the greatest physicist of his generation? Unfortunately, this was 20 years before relativity and quantum mechanics, so he was very wrong about the end of physics. So I think, and we don't have the end of physics either, because we have no theory of unification. We don't have quantum gravity. We don't, there's some very big physics issues that are completely on the table. So astronomy and physics are both teaching us that not to be complacent, because it's not over, and some big things we don't know, and some big things we may even have got wrong. So we shouldn't miss that. As far as beyond physics and the junction of belief and faith and science and so on, I do not practice faith, but as you know, I work with Buddhist, Tibetan Buddhists, and I've collaborated with Jesuit astronomers for decades. And they don't see any particular tension between the Jesuits, for example, between the fact that each one of them is a priest with a parish and a PhD astronomer. They live the double life, and it's fine with them. So, I think the tensions between science and religion are a little overplayed. And sometimes in the U.S. people do that for a particular reason. But there's some strains of conventional religion that probably aren't at odds with science. But most people of faith, in my experience, are quite accommodating of the amazing information of science and the mysteries there. So, yeah, I think there's plenty still to do. We're not at the end of the road by any means.
Yeah, so you see this combination is possible, keeping the mystery, keeping what is maybe precious to us, our stories, a little bit of mythology and God, they can exist together. Chris, go ahead, please.
Yeah, and the last thought, of course, is that in the vein of being humble in the face of what you do and don't know, it's just possible that as scientists, we may not be smart enough to figure this out. I mean, our brains have a certain capacity; they're pretty impressive, and we are creative. And we can be analytical, and we can do science. Uh, but some things may be beyond our grasp, and we might have to accept that. That's not a standard way scientists like to think. Scientists are optimistic. They like to think they can solve everything given sufficient time and resources. But it may not be true. And so we may just have to recognize our
But
own.
also standing in this century, all of this technology and science and advancement, it makes anyone be optimistic that we're just moving forward with the AI. I wanted to ask you about AI maybe shortly. What is your like? What are you excited about? Can AI any future discoveries for astronomy? What gets you excited?
I mean, I see the big strength and the big limitation of AI in my field. It's fantastically powerful for detecting things. We're dealing with a fire hose of data from these huge surveys. Astronomers essentially can't keep up. And so for discovering strange anomalous signals and looking for subtle patterns in huge amounts of data, AI is incredibly good. And it's done some amazing things in other fields than astronomy too. On the other hand, its limitations are also very clear. If you ask an AI to come up with a unified theory of physics that unites quantum mechanics and relativity, it can't do it, and it can't invent theories. It's just not good at the foundational creative aspect of science, and it may never, and it's not reasonable that it should, because all the AI's done is digested the entire internet and regurgitated it in different ways. So I don't see them being creative in that sense. That's an opportunity for science, of course. I mean, scientists are not going to be put out of business by AI, but it is a very powerful tool.
Yeah. Chris, thank you so much. It's been real pleasure talking to you. Thank you
Uh,
so much.
yeah,
And
Yazan, it was good to be with you. Great questions, and enjoyed the conversation.
thank you. Have a great day.